Rate of change. Our objectives in this lesson are to find the average rate of change of a function, use a graph to determine where a function is increasing, decreasing, or constant, and use a graph to locate maxima and local minima, use a graph to locate the absolute maximum and absolute minimum. Average rate of change is the ratio of the vertical change in y over the horizontal change in x between 2 points on a line. So the ratio is the rate of change. The ratio is how much you've risen from here to here divided by how much you've run from here to here. So we can call this average rate of change the vertical change divided by the horizontal change, or we can write it in function format more formally as f of x sub 2 minus f of x sub 1, all divided by x sub 2 minus x sub 1. In this example, I have the points -2, -1, and 4, 3. So I'm going to go ahead and let this point be my x sub 1 and my y sub 1. Here is my x sub 2 and my y sub 2. That simply means the x of the first point, the y of the first point, the x of the second point, and the y of the second point. So when I'm putting this into the formula, f of x sub 2 is 3. F of x sub 1 is -1. So I'm putting 3 minus -1. We'll need parentheses there. All divided by x sub 2. That's 4. And x sub 1 is -2. So minus a -2, again you need parentheses, and simplify. This is going to be 4 on top, a 6 on the bottom, which simplifies to 2/3. So our slope is 2/3. It's interesting to note that you could also use that simplified form to get this line, go up 2 and go right 3, and you'll land again on the line. You can use this slope as many times as you need. Up 2 more, right 3, and land on the line again. So an average rate of change divides the amount of change in the output quantities by the amount of change in the input quantities. The formula for finding the average rate of change might look familiar to you. That's because it is function form of finding the slope of a line. Now we say average rate of change because average rate of change applies to more than just linear functions. Okay, but we're finding the slope of the line that connects 2 points, and that gives us the average rate of change. So let's determine the average rate of change of the line passing through the points 1, 6, and -2, 0. Okay, so my average rate of change is equal to f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. This is my x sub 1, my y sub 1, or f of x sub 1. Here is my x sub 2, and here is my y sub 2, or my f of x sub 2. So I'm replacing f of x sub 2 with 0, subtracting f of x sub 1, which is 6, and dividing by x sub 2, which is -2, minus x sub 1, which is 1. This gives me a -6 divided by -3, and that is 2. So go ahead and graph the line, and you'll see what a slope of 2 looks like. And you can even count up to over 1. Up to over 1 as many times as you want, or from any point you could move down 6. 1, 2, 3, 4, 5, 6, and back 3. 1, 2, 3. Remember, your positive moves are going to the right or going up, and negative moves would be moving down or moving to the left, depending on if we're talking about positive y's, negative y's, or positive x's and negative x's. So let's look at some data on the cost of a can of soda for a few years, starting with the year 1980. In 1980, the price was 25 cents. 2004 went up to 50 cents. In 2018, we're at 34 cents. 2019, 35 cents, and so on, up to 2023 when it's 56 cents. We could look at the change in price from 1980 to 2003 in terms of dollars. Okay, so 56 cents minus 25 cents is 31 cents. So we could say that it changed 31 cents per can during that time. But another way that we could look at the change is by calculating the average rate of change during this time. So the average rate of change for that soda is, well, we'll go ahead and pull those points out. We have 1980, 0.25, and we have 2023, 0.56. So I'm putting that into my slope formula, my average rate of change. So we're finding the slope of the secant line through those two data points, or the slope of the line going through these 2 points. I have 0.56 minus 0.25 divided by 2023 minus 1980. Okay, and I'm going to have 31 cents. And then my years, 2023 minus 1980, that's 43 years. And I can put that into the calculator and divide, and I get approximately 0.0072. And so this is the amount of change in price per year. So this is in dollars per year for the average rate of change. In fact, if you would start with your price in 1980 and add this amount, try adding the unrounded amount that's in your calculator, add that 43 times, you would get to the cost of a can in 2023 of 56 cents per can. Here, the table gives the annual sales in millions of dollars of a product. So for example, we can see in 1998, the sales were $160 million. In 2002, the sales were $304 million. So the question is, what is the average rate of change in annual sales between 1999 and 2000 in millions of dollars per year? So we'll go ahead and make a couple of points out of those. We've got 1999, 214. We have 2000, 256. And our average rate of change is going to be 256 minus 214 over 2000 minus 1999. So 256 minus 214 is going to give me 42. I get 1 on the denominator, so it's 42. And so the average rate of change in annual sales between 1999 and 2000 is $42 million per year. All right. What about between 1999 and 2004? We're looking at those 2 points. So again, we can make our XY points out of those. And put that in our average rate of change formula. We have average rate of change is equal to 304 minus 214, all divided by 2004 minus 1999. So 304 minus 214 is 90. 2004 minus 1999, that's going to give us 5. And if we divide that, we're going to get 18. Okay, so again, the average rate of change can be stated as $18 million per year. So when you're writing this $1 million per year, it's giving you a ratio or a rate of change, and that is the average rate of change between those two particular years. Let's find the average rate of change from a word problem here. Noelle rides her bicycle for 8 hours and she's 34 miles from her house. Now after riding for 12 hours, she's 50 miles away. We want to know what is Noelle's average rate during her trip. So we don't know the entire data on the trip, but we do know that at 8 hours, she is 34 miles from her house. And at 12 hours, she is 50 miles away from her house. So the average rate of change is going to be 50 minus 34. That's the change in her distance, divided by 12 minus 8, the change in hours, so we know how many hours she was biking between these 2 points in time. So I have 16 divided by 4, and that is 4, and that is in miles per hour. Her average rate of change. How about we find the average rate of change from a graph? Here we want to estimate the average rate of change from x equals 1 to x equals 3. So at x equals 1, we're about right here. And at x equals 3, we're about right here. So we will have to give some kind of an estimate here. We're not given the formula for this graph. We're not given the output on the y-axis for the first point, but I do know the x is 1 and the y, let's say it's about 7.6. And our second data point is 3, 5. Okay, so we're going to find the average rate of change, 5 minus 7.6 over 3 minus 1. So this is a negative 2.6 divided by 2, which is negative 1.3. So remember, you're finding the slope of the line that goes between those 2 points. Let's see. Does it seem like it makes sense? A negative 1.3 and over 1. A negative 1.3 and over 1. Definitely looks like that. It's definitely a negative average rate of change as well. Let's find the average rate of change of a function. So here we've been given the defined functions f of x, and they have an interval that they want us to find the average rate of change over. So we're looking at an x sub 1 of 3, and the next time that we're looking at it is this x sub 2 of 5. So we have our x sub 2 and our x sub 1, but we need to find the output of those values. So that'll be the first order of business. We're going to take f of 3, f of my x sub 1, put that in. I've got 4 over 3 times 3 minus 1, so that's 4 over 9 minus 1 is 8, which is 1/2. So I know I have this point of 3, 1/2. F of 5 is equal to 4 over 3 times 5 minus 1. So 4 over 15 minus 1 is 14. That gives me 2/7. So 5 2/7 is the other point. And now we find the average rate of change between those 2 points. I'm going to have 2/7 minus 1/2 divided by 5 minus 3. Okay, and I know this is an ugly fraction, but we could multiply by 14 over 14, and that would clean things up quite a bit. All right, 14, I get that from looking at the little denominators here of 7 and 2. And so if you want to get rid of those little denominators, multiply by the least common denominator of those and do it on top and bottom so that you're just multiplying by 1. Right, 2/7 times 14, well, 7 goes into 14 2 times. 2 times 2 is 4. Minus 2 goes into 14 7 times. 7 times 1 is 7. Over, here I have 5 minus 3 is 2, and 2 times 14 is 28. This gives me a negative 3 over 28. And that's our average rate of change over that interval. Okay, on this one, f of x is 9x squared minus 5, and I'm finding the average rate of change between 2 and a. All right, so f of 2 is 9 times 2 squared minus 5. 2 squared is 4. Times 9 is 36, minus 5 is 31. So my first point is 2, 31. And then f of a is 9 times a squared minus 5. Well, it doesn't really simplify it. It's just 9a squared minus 5. So our second point is a, 9a squared minus 5. And now I'm going to find the average rate of change between these 2 points now. I have here 9a squared minus 5 minus 31 over a minus 2. Simplifying from there, I get 9a squared minus 36 over a minus 2. And yes, you will end up with a variable in your answer. Let's find the average rate of change of this function f of x equals x squared minus 3 on the interval from 2 to 2 plus h. Just as in the previous examples, they're giving you the x sub 1 and x sub 2. And we want to find f of x sub 1 and f of x sub 2. So f of 2, our x sub 1 that was given, is 2 squared minus 3, which is 1. That results in the coordinate 2, 1. This is our x sub 1, and this is the y sub 1, or f of x sub 1 that goes along with that input. Our next input is 2 plus h. So f of 2 plus h is, here's a time when it could be helpful to write this as a template. And the input is 2 plus h. 2 plus h quantity squared minus 3. We do have to simplify. I have 4 plus 4h plus h squared minus 3. And that equals, in descending order, h squared plus 4h plus 1. This gives us the coordinate 2 plus h, and h squared plus 4h plus 1. Just like above, this is x sub 2, and this is our y sub 2. Then we'll find the average rate of change, or the slope of the line between those 2 points. We have h squared plus 4h plus 1 minus 1 all over 2 plus h minus 2. So this is h squared plus 4h over h. Now that I have it down to this, I see my h squared and my 4h can both be divided by h. So I take the one more step and I get my average rate of change of h plus 4. Now on increasing and decreasing intervals. We say a function is increasing on an interval if the function values, the y's, increase as the input values increase within that interval. Similarly, a function is decreasing on an interval if the function values, again they're saying the y values, decrease as the input values increase over that interval. The average rate of change of an increasing function is positive, and the average rate of change of a decreasing function will be negative. Here, you can see we're always going to describe these intervals in terms of x. So we can see here that we are increasing on this function until we get to here. Okay, so this interval from negative infinity until negative 2 is increasing, and it happens again here. We have been falling, and then all of a sudden we are increasing again. So we're increasing from an x value of 2 on. So there we go, our second interval. Where are we decreasing? Well, we're going to be decreasing from here, this x value, to here, this x value. So we're decreasing on negative 2 to 2. And these will always be parentheses on here. You're never going to see square brackets because we're talking about open intervals. And if we were, let's say that if we were to include this point just because, well, it's a solid dot, well, do you include that solid point here and on here? Because then the number 2 is both increasing and decreasing. And it's silly to say that a single number is increasing or decreasing anyway. Only the interval can be increasing or decreasing. With this last example, we're given a graph and we're to find local extrema and absolute extrema first. Local extrema is any place where you see kind of a high or a low point. And it doesn't have to be the highest, it doesn't have to be the lowest. It just has to be some place where you see a little high in its little neighborhood of points. So, for example, if you look at this little neighborhood of points, this guy here seems to be the high point. Look in this neighborhood of points, this guy seems to be the high point. And if you look in this little neighborhood of points, this looks like the low point. So we have some local extrema. They are the extreme ones in their area. We'll just kind of guesstimate what those are. Okay, so we have local minimum, a local minimum of 1, -4. We have local maxima, that's plural for maximum, local maxima of -2.8, we'll say 8, and let's say a 4, 10. So those are our local maxima. Now, any absolute extrema means the absolute highest point, the absolute lowest point. So when we are looking for absolute minimum, looking for the absolute minimum, there actually is no absolute minimum. Here is that local minimum that we talked about before, but you can see this arrow here and here. Those indicate that the function continues to travel down, and so it's never going to have a lowest point. There's always another lower point and another lower point and so on. So absolute minimum here is going to be none, and absolute maximum, we have just one absolute maximum, and it's between these two here, and we can see this one is the higher, so it is the absolute maximum, and that was at point 410. Okay, now find the intervals here again just for practice where the function is increasing. Looks like we're increasing from -infinity until about -2.8, and then we're increasing again from 1 until 4. And for our decreasing intervals, move down to that part, the decreasing intervals, well, that's going to be from -2.8 to 1, and from 4 to +infinity. And the last question on here, find the domain and range for the function. So remember, the domain is what x's, all of the set of x's. So this is going this way forever, which means it's going to continue to cover all these x's, and this is going this way forever, which means it's eventually going to cover all of those x's. So our domain for this function is going to be from -infinity to +infinity. The range, just like in domain, we read from left to right, from negative x's to positive x's. We're going to start down here and read up. So we're reading from negative y's to positive y's. So my lowest y I see, well, this again, it continues. So it's coming from negative infinity, and the highest value that it reaches is right here at 10. Right there at 10. So the range, the y's that are used are from negative infinity to 10, and that is a solid point at 10. So we want to include the value 10 in that interval. And that does it for this lesson. You're ready for your homework.